Thanks for having me come talk. I actually have this presentation. I've given it a few times before to various groups, much like yourself. Master naturalist groups typically see part of this presentation. I'm going to talk about weather, climate, and then we're going to touch a little bit on climate change toward the end of it. So, like I said, my name's Ted Ryan. I work for the National Weather Service in Fort Worth. For those of you that don't know, we were formerly the Weather Bureau, but we changed the name to the National Weather Service many decades ago, but some people still do call us the Weather Bureau. We're a federal agency. We're under the Department of Commerce. We essentially provide the radar, satellite, and computer modeling for weather forecasts and climate forecasts to both public and private weather enterprise. A little bit more about the Weather Service. We remain essentially a 24/7 weather watch over the entire country. That means we all work shift work, and we're always there. At least 2 meteorologists are always staffed at all times. We issue the weather warnings, so you hear about tornado warnings or severe thunderstorm warnings. That's us. Public forecasts, aviation forecasts, fire weather forecasts. We assist with any hazardous material incidents that may occur. Fort Worth office, just so you know that you're kind of special here in Tarrant County, that the Fort Worth office is located in Fort Worth, but we actually cover 46 counties in north central Texas. We're one of 122 such offices around the country. So the office in this region is in Fort Worth. It's not in Dallas, and the reason why it's in Fort Worth is that's where the oldest weather observations and Weather Bureau was started back in the 1880s, I believe. So it's been long running that Fort Worth has always had the weather station. A little outline about my talk as we go through it. I'm going to talk about what weather is and what climate is, and specifically what the difference between those two are. And I'm going to talk a lot about North Texas climate, which I think we all would find interesting to us since we live here. North Texas climate covers a lot of things, including drought, ENSO. I'll explain what that is in a little bit, and I promise you've already heard of it before, and other what we call climate oscillations. And then we're going to touch on climate change. And I can promise you that probably whatever you've heard on the news or seen on the internet is, I like to call it's junk climate change talk. It's pop science, so to speak. There's a lot of misconceptions out there about what climate change is and is not from both sides of the political spectrum. So I'm going to be here and tell you just exactly what the science says, and we can talk a little bit about that if you have some questions about that toward the end, because most people do have questions about that. So let's start off. Well, what is weather? And I'm talking, big, large scale picture here, a 30,000-foot view. Weather is just simply the redistribution of heat from an unbalanced state to a balanced one. And that's just a fundamental law of thermodynamics. Now, that sounds like a definition of weather you probably never heard before in your life. But all weather is basically heat is moving from one part of the earth to another part of the earth. So I have a picture of a hurricane here on the right side. And basically what a hurricane is a giant heat engine. And what this does is it transports heat energy from the warm ocean waters into the atmosphere, and then often sometimes up into the polar regions. And so this heat engine, what is doing is redistributing heat from a very hot part of the earth to a very cold part of the earth. And so all weathers, essentially all wind, all weather systems, all they're doing is redistributing heat around the earth. So because the sun is continually shining on our earth, and the earth is continually rotating, and our earth is covered with oceans and land masses with forests and deserts and mountains, all of which heat up at different rates, the earth is forever in an imbalanced state of heat. So what that means is, as long as the earth is rotating and the sun is shining, we will always have weather on earth. It's a constant game that the sun and the earth are playing with each other, that the sun heats up the earth differently, and then the earth is trying to redistribute that heat, and that redistribution of heat is what we call weather. So I don't have a lot of time today to actually go into a little bit about weather. If you're really interested in weather, I would strongly recommend that you go to this website here, weather.gov/jetstream, and it's an online school for weather, and you can see here on the right-hand side all the topics you can read about. You can just pick a couple if you're interested. If you want to go through the whole course, that'd be great too. But it's a really good kind of no nonsense, very basic understanding of what weather is. So I know a lot of people tend to be interested in weather, and I definitely would encourage you to go visit that website for more information about weather, on a day-to-day basis, and what it is and what it is not, so to speak. So the big question then is, what's weather and what's climate, and where's the distinction between the two? So weather is driven by those localized heat imbalances from day to day, and that's the big key here, day to day. Those heat imbalances are influenced by the laws of physics. What that means is the sun is shining outside right now, and the sun is heating up the ground actually, and the ground is actually what heats up the air. Those are all just laws of physics. When that air heats up, it may have a lower or higher pressure than the air next to it, and that air may move toward low pressure. And that's, again, it's laws of physics, it's fluid dynamics. That's generally what we go to school to learn, or how the air moves around, so to speak. So there are annual cycles, as we know. Those are like the seasons, as we call them, and those are astronomical influences. So the Earth is rotating and it's moving around the sun, so to speak, but it's also tilted on an axis about 23 degrees. And that tilted axis causes our seasons, and that at certain times of the year and certain hemispheres of the Earth, the sun is more intense, and so it's hotter, or it's less intense, and so it's colder. That's an astronomical influence that is a seasonal thing. That is not necessarily climate in itself. That's just a 1 year period. That is just something that always shows up in our climate record. Climate is average weather. And it's interwoven. All the things that we know about science, so to speak, go into what climate is. It's astronomical influence. There's ecological influence. There's geographical influences. There's physical influences, and there's chemical properties. All of those influences and properties, and all the things that we like to call science, we break science off and say, this is biology, this is physics, this is chemistry, this is this is astronomy. Climate actually gathers in little pieces from all of those fields, and we have to know a little bit about all that stuff in order to determine how to predict the climate, so to speak. So climate is a very high level science, so to speak. Meteorology, or how weather forecasting, is actually a very young science as well. Many people are probably surprised to learn that we didn't even know jet streams existed until World War II. They were flying missions to Japan, and they would get caught in these wind currents where they were flying at 100 knots, but they were actually going backwards. And so they were discovering the jet stream back in the 40s. It wasn't until 1960 that we had our first satellite. And we actually got to see how clouds looked and across the entire world, and how organized the systems actually were. Really, radar didn't come along until a little bit after World War II. It wasn't until the 50s, 60s, and 70s that we actually tried to start predicting weather with computer models. And so really, I like to say the modern age of meteorology is really only about 50 or 60 years old. And so when you complain about why the forecast is never right, just remember that it's really a very young science compared to chemistry, astronomy, physics. Those are very old traditional sciences. So is it weather or is it climate? It's a tough question to answer. I do like to say that weather is one's mood, climate is one's personality. I think that's a great analogy to explain what is what. So weather being one's mood, you can think of somebody that, is a very cheery person. They may have a bad day. It's nothing out of character. But you can also think of somebody that's, very cheery, and there are things that they just would never do or would never say. So we know some things about the weather because we know some things about climate. So like we know that it'll never snow in Tahiti. Tahiti just is incapable of having snow. So that climate, so to speak, can help us predict the weather. Now here in North Texas, I like to say that our climate is very bipolar. As you know, in February it was extremely cold, and then just 5 months later it's extremely hot. We can have very wet years, we can have very dry years, we droughts and all that stuff. So, but that kind of bipolar mood, so to speak, is our personality. And now our weather may be a little bit more difficult to forecast because of that. So I've got a little map here, and when I say weather is, the day-to-day stuff, and climate is the personality, we've all heard of Tornado Alley. A tornado alley obviously extends, near our region up into the plains. And all the things that go into making Tornado Alley part of the climate, so to speak, are things that govern the weather and the climate. So the ingredients that you need for a tornado alley, so to speak, are all in place over the United States. In fact, the United States is probably ground zero for the most tornadoes anywhere in the world. So, and it's not just because, that's just how it is. It's because of the way that our geography is set up to actually create that type of climate. So for tornadoes to form, we have many ingredients. One of those is we need cold air coming down from the poles, and that's ingredient one here. The second ingredient is we need a jet stream. The jet stream usually only exists over certain latitudes. The jet stream also needs to be wavy, so to speak. In the northern hemisphere, the jet stream is very wavy over North America. If you were to go down into the southern hemisphere, the jet stream actually is very, very unwavy, and it doesn't travel in waves down the southern hemisphere because there's not as much land. There's actually more water down there, so the jet stream tends to be more flat. The third ingredient for tornadoes to form is we actually need warm, dry air coming in from the desert of the Southwest and the higher terrain over Mexico. That creates what we call the cap. You might have heard that term on television weathercast before, but that's an important ingredient for tornadoes to form or tornadoes to be frequent. And then finally, we need warm, moist air, and that big Gulf of Mexico to our southeast provides that final ingredient. So weather, once again, would be whether or not we're going to have tornadoes today or tomorrow or next week. Climate, though, is this specific region tends to see tornadoes over the course of years or decades. It just tends to frequently occur over and over again. So one of the great things about climate is we don't have to know a lot of things about what the weather is. In fact, if we had gotten a plane and were just dropped off somewhere, what we could do is we could, anywhere in the world, we would look at what was growing and we would know a lot about the climate. If you got dropped off in a jungle, you would know, well, this is a jungle. They probably see a lot of rain. They have warm temperatures. There's lots of tropical plants here. Likewise, if you dropped off in a desert, you would look around and see what was growing there. And just by seeing what's growing, you can determine what the climate is. So even on a day where you have maybe really warm temperatures on the top of a mountain, you could look around and say, well, there's nothing growing here but some scrub brush. This must be a very hostile climate. It must be very cold in the winter. Even though the weather that day might not tell you exactly what the climate is, the plants that grow in a certain region definitely do. So over the United States, this is the same climate classification map I showed you for the whole world. We have some distinct zones, and I think many of you are familiar with kind of how the vegetation across the country looks. There's lots of trees and stuff all on the East Coast. There's lots of deserts and scrub across the West. In the mountains, you have kind of mountainous terrain. Up north, there's pine trees up in northern Minnesota and Wisconsin. But I guess coniferous trees. I don't think there are technically pine trees up there. Pine trees in East Texas, at least. For us in Texas, we're kind of broken down into 4 of these climate classifications. Now, most of the state is called this humid subtropical, meaning we do have some trees. It tends to be humid, as we know. Subtropical, meaning that it's generally warm, but we do have some instances where we do get below freezing, so to speak. So we don't have tropical plants here. Across the western part of the state, there's what's called kind of this mild steppe, meaning that's not many trees. This is kind of the area from Amarillo to Lubbock to Midland. You probably know right away if you've been out there, there's just a lot of grass growing there. It's called the mild steppe, not that it doesn't get hot out there, but they do get very cold. In fact, they can get down, below zero, and Amarillo especially. So it's not tropical by any means. There's the hot steppe, which is kind of from Midlands area south, all along the Rio Grande Valley. That's kind of a lot of grass growing in that area. It's a hot steppe, and that temperatures don't get as cold, so there's a lot of cactus type plants growing there. And then finally, there's a little sliver of some Highland climate classification in our state. If you've ever been out in the Davis Mountains, Guadalupe Peak, so to speak, once you get up at higher in those higher elevations, you get lots of pine trees and stuff that isn't growing around there, but that's because, again, the climate is different on the top of those mountains. So daily weather records eventually become climate records. And so for many, many centuries almost, humans have been recording the weather. Ship's logs, they just would write down what the temperature was, what the pressure was, generally what the wind was, what the character of the weather was. And so those records, over time, they start to add up and they mean a lot of things. So for our area in North Texas, this is the temperature climatology for an entire year. If you take enough records, in which we have been doing essentially from 1900 all the way to present date, you can start to kind of construct a temperature record that looks like what your climate looks like. So this is our temperature record, and I'll explain this briefly. Obviously, the date here, the day and the month of the year is here on the bottom. So the temperature, which is shown in the reds or blues here, reds are high temperatures, blues are low temperature dots here. Obviously, our summers tend to be warm, or our months from June to July, August tend to be warm. And our months in the wintertime tend to be cold. That's no shock to anyone here. But what's interesting about the climate record is the dots show our normal temperature, while the little squiggly lines at the top and bottom are our record low temperatures. The shading is what we call one standard deviation, meaning that 90% of the time the temperature is going to be, the high or low is going to be inside these blue or red shadings. So some things that are interesting about our climate. We are currently at the hottest part of the year here, August 5th or so. This is about as hot as it gets normally. As we know that it's not quite that hot today, but it'll be hot again, next weekend. But we can expect it to be hot this time of year. What's interesting is that the record high temperature this time of year is really only about 10 degrees higher than our normal high temperature. So there's a very much more compressed or smaller range of what the temperature does in the summer versus what it does in the winter. You can see that in the winter time, our normal high may be 55 degrees at DFW, but our records can still hit 90 degrees. So it's no longer just 10 degrees away from from the normal high to the record high. It's something like 30, 35 degrees, which is a big jump. You'll notice that the shadings actually overlap here, meaning that in the winter, it's hard to say what is normal. It can be very cold or it can be very warm, but both are possible. That doesn't mean that there's climate change or extreme weather or anything like that. That is just a part of our climate, that our climate can be highly variable, especially in the winter time. So with low temperature records all across the country, you can compile these maps called let's see here, these hardiness zone plant maps. And I think we've all seen these before. A lot of us use these to decide what zone we're in. If we're 7A, 7B, we should only plant 7A, 7B, and on up type plants, so to speak. And on down type plants. You wouldn't want to plant an 8A plant here in our area, because a big freeze like what we had in February comes along and it actually would kill it off. So in our region, and what these maps are compiled upon are the climatological, what they call, kind of mean worst case low temperature scenario, right? So 7A is between 0 and 5 degrees Fahrenheit, above 0, and 7B is 5 to 10 degrees Fahrenheit. Now, there are a lot of people in our area that I think were planting things that were, 7B, so to speak, with the assumption that we would never be below 10 degrees. I think last February, we all learned that, it can get much colder than zone 7B here. And I think a lot of us lost some of the plants that we were growing. And I remember looking at these charts, and I know it's going to seem kind of like no duh when I tell you this now, that, I had always expected that at some point our climate would produce a 6B type freeze event. And why would I say that? Well, we had one in 83, we had one in 89. We had one, I think, in 49. There was one in 1899 as well. So we obviously had another one this year. So I would give this talk, a couple of years ago, and I would say eventually the lakes will freeze again. There will be below 0 temperatures in our region, and people would I would say there would be another caliber 83 or 89 type freeze event. So that absolutely did happen in February. That doesn't mean that the weather's getting worse or that it's getting more extreme or that was a result of climate change. That is a part of our climate. Our climate produces these record cold snaps, so to speak, where we get down near 0 degrees or colder about once every 50 years, once every 30 years, so to speak. Doesn't mean we're not going to have one next year. It just means in an individual year, we have about a 2 to 3% chance that we're going to have temperatures near 0. So that is just our climate. Now, if you were asking, well, if climate change is going to influence that, what we'd have to look at is like perhaps 100 years worth of data, so to speak, to know that that frequency is either increasing or decreasing. We can't just look at one event and say that, oh, well, this one event happened, it must be climate change. And that's absolutely not true. What else can we do with climate data? Well, we can plot all the average rainfall for all the stations in Texas on a map, so to speak. And here's the average rainfall for Texas. And you'll notice as you get into East Texas, there's certainly 50 or almost 60 inches of rain that occur every year on average. You get out into West Texas near El Paso, it's less than 10. And I think if you've ever driven across the state, you know that, again, by looking at what's growing in that area, you can tell exactly how much rain there is or is not. I see my cat has joined the talk. So the other thing that we can do is look at record events. This is my favorite snowfall event. This is an event in December 21st, 1929. You'll notice up here, this is Tarrant County. When we just got a trace of snow in this event, but if you were to travel down south to Hillsborough, you would notice that they had over 26 inches of snow in one day. And so that's just an insane amount of snow when you think about all the snow events you've seen here. But what this tells us, and what this extreme climate event here tells us, is that eventually someday we're going to have another snowstorm that's going to produce 2 feet of snow somewhere across North Texas. That may seem, just ridiculous, but I'm telling you, if this happens in the next decade, I want you to think about what I said. Say, well, that weather guy said eventually this would happen. And I promise you, when it does happen, there are going to be people out there screaming that this is climate change and that the 2-foot snowfall that fell over Dallas was proves climate change or whatever it is. And again, that's not how this works. Having a 2-foot in a day snowstorm is part of our climate record, so therefore we can assume that it'll probably happen again sometime. One of the other big topics is tornadoes. Tornado Alley. We talked a little bit about Tornado Alley. We have recorded all the tornadoes that have occurred essentially since 1950. Across each county in North Texas, and we can look at the strength, the magnitude, and the length, and glean a lot of information about what time of year these form and how they tend to be, et cetera. So climate isn't just about what the temperature is, it can be about what the rainfall is, what extreme events you have as well. The other thing we can do with climate data is we can plot it on a axis. So here is all of DFW's annual precipitation from 1900 to 2020. And on the bottom, it starts at 1900, goes all the way to 2020 on the right side. So right away, before I show you anything, you'll see how variable it is from year to year. That our climate, so to speak, can vary as much as from 20 inches to 40, 50, and then even a few years ago, we had over 62 inches, which was our highest rainfall on record. I think a lot of us remember 2015. It just wouldn't quit raining that year. And we always set the yearly rainfall record that year. The other thing that we see here is we can find areas where we have a really low precipitation. 1921 is our record of 17.91. That's not a lot of rain, as I'm sure you're aware. There's also some big periods of drought, multi-year drought. So here's the 50s drought. I don't know if any of y'all are old enough to remember the 50s drought, but the drought in the 1950s was Texas's sort of benchmark for the worst drought that we have experienced. We had another bad drought back in 2010, 2014. I think a lot of us remember that drought and what that did to our water resources and our area lakes. What the meteorologists were saying at that time was actually this wasn't near as bad as what it was in the 50s. So what we can glean from this information here is that drought is a part of our climate record, and multi-year droughts are a part of our climate record. The other thing that we can look at here is if we put a trend line of the precipitation, one can make an argument here that DFW is getting wetter. You'll notice back in 1900, the average precipitation was about 30 inches per year, and it's increasing up towards upper 30s, maybe even up to 40 inches per year now. So that's an interesting thing that we can see in our climate record. Does this prove or disprove climate change? We'll talk a little bit about that in a bit. We can do the same thing with temperature. So here's the DFW's average temperature, again, from 1900 to 2020. You'll notice our average temperature is about 65, maybe 66 degrees. It would be nice if the temperature was that, year round, so to speak, but we know that our climate is actually that in the course of a given year that we have temperatures wildly around that. But if we were to average all the highs and lows for an entire year, that's what our average temperature would be. What we'll notice here is the 30s were a very hot decade for DFW and much of the United States. When we had the 50s drought, it was also very hot, and that's because when you have a drought, you tend to have hot temperatures that also accompany it. The 70s were a very cold decade for DFW. DFW actually had a lot of snow in the 70s. Just every year we had many snow events that occurred in the 70s. So 70s were a cold decade for us. Now, I can put the same trend line on here and say, well, is DFW getting warmer? And I think we would all agree that the trend is generally up, and we'll talk a little bit about that in a bit. But what I really want you to notice here is there's actually a signal in here where there is a oscillation of the average temperature that takes about 60 to 70 years to complete. Meaning that we'll have hot decades and then we'll go into cold decades about 30 or 40 years later, and then we'll go back into hot decades and then cold decades follow that. So that's very interesting. That's what we call these climate oscillators that impact our weather essentially from year to year and decade to decade. And I'll explain what those climate oscillators are. El Nino, La Nina is the big climate oscillator. We call that ENSO. It stands for El Nino Southern Oscillation. The reason why it's called the Southern Oscillation is because it's actually the pressure difference between Tahiti and another point in the Southern Pacific Ocean, where they compare that the pressures are higher or lower, and then as they become higher in one site and the other site becomes lower, what that is an El Nino or a La Nina event. The El Nino events are all the events here in the last 60 years that are pointed here in red. Those are El Nino events. All the blue events up top are the La Nina events, so to speak, when the oscillation is on the positive side, so to speak. You'll notice that there's a trend where we even have El Ninos and La Ninas tend to be more or less frequently. Again, there's another oscillation that's going on here. This one is a very long period oscillation, maybe 10 years, maybe 50 years. We'll talk about it on a later slide. So here is what El Nino conditions look like. What I've got here is the Pacific Ocean. On the right side is South America. We're kind of located up here on the upper right corner. On the left side, this is Asia. There's Thailand, Australia. The map is the color of water temperatures that occur in the Pacific Ocean. And so what happens in an El Nino year, we actually have a relaxing of the trade winds, which causes the water temperatures to increase in temperature over the Pacific Ocean, the equatorial Pacific Ocean. And that creates thunderstorms and rain and all kinds of stuff along the equator in an area that's not usually seen that type of weather. When that occurs, what happens is the subtropical jet stream, which you probably heard about on the news, the El Nino subtropical jet stream becomes much more active. And what we see actually is cooler and wetter weather over the southern part of the country, or our area, so to speak. Otherwise, the rest of the country tends to be a little bit warmer and a little bit drier. And that's because the polar jet stream is actually located farther north and is much weaker in an El Nino year. So that's why we talk a lot about North Texas, whether we're going to have an El Nino year or a La Nina year, because there is impacts on our weather. We're one of the areas in the country that get this cooler and wetter weather whenever we have an El Nino event. Okay, so here's the La Nina conditions. And what happens in La Nina is that the trade winds tend to blow much stronger than what they usually are. What this does is it pushes that thunderstorm activity well across into the Western Pacific Ocean, where that stuff is located there. And we actually see sinking air kind of over our region of the hemisphere here. The stronger trade winds, what they do is they actually bring up the colder water from the depths of the Pacific Ocean, and they cause a cooling on the surface waters. Here's what the La Nina pattern tends to look like. We get this big blocking high pressure system. The Pacific or subtropical jet stream tends to be much weaker, tends to be much more variable. Because of this blocking high system, the polar jet tends to be stronger. It brings a lot colder air into that part of the continent up there. And our weather here tends to be dry and warm. Dry and warm tend to always go together. If it's dry, it's usually going to be warm because your daytime highs are going to be much warmer. So let's summarize what ENSO does to Texas weather. So El Nino winters, wetter than normal, mild or near cooler than normal temperatures. And that's because we tend to be wetter than normal. Our high temperatures tend to be cooler than normal. And so that the average tends to average out. We don't tend to be really cold or have really cold outbreaks in El Nino winters. For La Nina winters, it's drier than normal and we have above normal temperatures. And that's usually because there's not much precipitation. Every day tends to be sunny. We get a much warmer high temperatures. For neutral winters, meaning winters that aren't El Nino or La Nina, near normal temperatures overall, whatever we classify that as, but we have noticed that we have more extreme cold winter weather events, cold winter events. We get these really big Arctic surges and neutral winters. So what are we expecting next year? Looks like we're expecting a La Nina. Right now, it's still kind of in the cards whether we're going to have a neutral winter or a La Nina. It looks like we are definitely not going to have an El Nino winter this winter. Okay, so let's talk about one of these other oscillations. I mentioned that there's 50 or 60 or 70 year oscillations that occur that impact our weather. One of those is the Pacific Decadal Oscillation, which we call the PDO for short. Now, this looks at temperatures that occur in a certain part of the Pacific Ocean and compares how it works for the entire climate record here. You'll notice that when the cycle for the PDO takes about 50 years to complete, meaning that it goes in the cold phase and then it goes in the warm phase and it goes back in the cold phase. It takes about 50 years for that to occur. What happens is El Nino tends to occur more when the PDO is in the warm phase. As you can see here, when the warm phase, we have 10 El Ninos and only 3 La Ninas. And the cold phase, we had 7 El Ninos and only 14 La Ninas. So now that we're back in the cold phase, and we've been in the cold phase since 1999 or so, and we probably will be for probably another, I don't know, 5-10 years or so. We'll see how it goes. We get more La Ninas, and that has been the case since 1999. We've had a lot more La Ninas than we've had El Ninos. This map here actually is the the PDO oscillation for from 1950 to 2020. And you'll notice again, we are in this cold phase here. You can see the sine wave here showing the cold phase. So we're in the cold phase, meaning La Nina is more likely. But you also notice that doesn't mean that we don't occasionally flip back to a warm, or in the cold phase have a period of cold weather as well. But it does make it more or less likely, so to speak. One more oscillation. I'm not going to talk about all the oscillations because there's literally dozens of them and we don't have time to talk all about them, but these are the ones that tend to impact our weather the most. And I think you'll see real soon why I'm spending time talking about all this stuff. So there's the Atlantic Multi-Decadal Oscillation, which is called the AMO. What this is the water temperatures in the Atlantic Ocean. This one is about a 60 to 80 year period, meaning it takes 60 to 80 years to go from the cold phase to the warm phase, the cold phase to the warm phase. This is all the way back, this data goes all the way back into the 1850s. And that's because humans were recording some of these temperatures. We had a lot of shipping back then, and we knew what the water temperatures were way back in the 1850s. So this is a very old one. What they notice with this phase is that hurricane activity tends to be much higher when the AMO is in the positive phase. You'll notice we're in the positive phase now, and we have been since about 1995 or so, and we've had very active hurricane seasons. So a lot of times you'll hear on the news that we're having more and more hurricanes, and yes, we do have active hurricane seasons, but it doesn't mean that it's necessarily climate change. In fact, the AMO is controlling the number of hurricanes way more than climate change is, and I'll get into that in a little bit. But the AMO and the PDO actually influence Texas weather. You may already remember looking at this slide that I told you that the 30s and the 50s were very warm decades. When we're in the warm AMO cycle, Texas tends to have a warmer than normal cycle, and that's kind of almost closely mirrors what that little DFW climate trend I was showing you before. So Texas weather, we can look at both the AMO and the PDO, and when we sync them up, it actually turns into a very strong drought indicator for Texas. So back in the 50s, we actually had a warm AMO. So when we have a warm AMO and a cold PDO occur at the same time, very strong drought signal for Texas. So our worst drought on record, both the AMO was in the warm phase, the PDO was in the cold phase. That drought we had back in 2010 to 2014, same thing. AMO was in the warm phase, PDO was in the cold phase. And you'll notice this doesn't sync up all the time. There are some instances where we have we have those conditions show up, but we don't have a drought. But you'll notice that our big droughts multi-year droughts do tend to follow this pattern. So this is important now because we are generally in a cold PDO phase, and we are generally in the warm AMO phase at this time. And we may be for another 5 to 10 years, meaning that we're very close to slipping back into another multi-year drought that could be pretty bad. So that's just one thing to keep in mind as we go from season to season and year to year, is that at least in the next 5 to 10 years, we may have another really bad stretch of drought conditions that stretch many years. We can also look back centuries. So we only have weather records for Texas really from start of 1900, so to speak. But we can look back centuries by examining tree ring data. This is a very noisy, complex graph. And what I'll say that basically this graph from about 1700 onward, or the last 300 years or so, we have a lot of what are called tree ring climatologies to make a really good guess of what Texas's weather looked like. As you know, there aren't a lot of trees that are older than 300 or 400 years in Texas, and the record for trees that we can look at starts to get very regionalized. So I wouldn't pay much attention to this side of the graph. But certainly in the last 300 years or so, we can see how the drought and how the rainfall patterns looked in Texas. So this red line is kind of, you can see the cycle of drought and wet years. Droughts are the negative part of the graph, and the wet years are the positive part of the graph. So to take away from this, you'll see the 1950s drought here. We had, very strong drought indicator in the tree ring data here, but it wasn't near as bad as what we had in the 1850s. And then it looks like there was another really bad series of drought in the 1700s, sometimes 1770s, maybe. Hard to say exactly from this graph. The other thing to note is that in the last 50 years or so, maybe 60 years or so, we are currently in the most drought-free period of the last millennium. Yes, we had the 2014 drought, but our years have been getting wetter and wetter. So that may be something to think about, especially when you talk about water needs of a population, that if this is the wettest time we've been in the last millennia, maybe that's not good. Maybe when drought comes back around, we're going to run out of water in Texas. So we should be doing things to plan for that. So let's talk about drought and climate change. So I want to just stress here, drought has always been a part of Texas climate. If you've been here for 56 years, you know that it seems like we're always in drought except when we're flooding. And I do like to kind of joke with people that Texas or our region always is in drought, and it's just broken up by periods of extreme rainfall and floods. That's just our climate. So regardless of climate change, droughts are going to occur. That's not going to go away. Droughts are a part of our climate. They're going to continue to occur. So the issue really becomes the increasing population, the impacts of drought may become more severe because we have more population, more people need to have water, and perhaps multi-year droughts would deplete aquifers or surface water reservoirs. This is a picture of Lake Granbury back in the 2010 to 2014 period. I think this was about 2014. Obviously, you can see that the water is supposed to be much higher, and it's not. So when we get into these multi-year droughts, this is the kind of stuff that we expect to see. If temperatures are increasing, meaning that if it's getting hotter, it'll make droughts worse. And the reason why is because droughts and hot temperatures tend to feed back on each other. When you have really hot temperatures, you tend to make droughts worse, and you make the ground drier, and the dry ground actually heats up faster, so that when the sun comes out again, it makes it makes the temperature hotter, which then evaporates more of the water, surface water, and it kind of feedback loops on itself. So droughts and hot temperatures tend to go hand in hand, and it's because they both kind of help each other be the best they can be, so to speak. Okay, so let's talk about climate change. And I understand this sometimes can be a sensitive subject to many people. I'm going to state right away, I'm not a climate scientist. I am a meteorologist. I do follow the field pretty closely. I can, again, promise you what you've heard on the news or maybe read in articles or newspapers is a lot of pop climate change science. That's not real science, so to speak. And the reason why is because there's an impression that there's a lot more answers out there than there actually are. You'll notice, is the climate changing? And so to start that question, we'll have to ask, well, how is the climate changing? How much is the climate changing? What's the historical context? I spent a lot of time talking about the whole historical context of Texas weather. That stuff's important. You can't just look at one year and say, oh, well, this big cold snap proves or disproves climate change. You absolutely can't do that. You have to have a really long historical record to know those types of things. How much of the change is a result of human activity? That's probably a big question I want to know. If the climate is changing, well, is it because of what humans are doing? If not, then then there's nothing we can do, right? What will happen in the future? Do we understand how bad climate change will be? If it's good or bad for us? What can we do about it? So you notice this slide, there's a lot of questions that are really nuanced questions, but they're extremely important to answer if we're going to have a good, honest discussion about climate change. So let's talk a little bit about climate change. And so again, 30,000 foot view, what we're talking about here is Earth's energy balance. And what that means is when the sun is shining, 100% of the energy coming to Earth, about 30% is actually reflected by clouds or the Earth's surface. The other 70% of the sun makes it to the ground or is absorbed by the atmosphere. What happens then is that the ground actually radiates that energy back to space. Because that radiation that comes from the sun is a shortwave radiation, meaning a high intensity solar radiation, and the ground's radiation tends to be a long wave radiation of a very, very low intensity heat radiation, a lot of that radiation is absorbed in the atmosphere, and the atmosphere absorbs that radiation and sends it back down to the surface, meaning that there's the surface continually has this. So what I'm talking about here is the greenhouse effect, is that we call it the greenhouse effect because, greenhouses tend to be warmer than the outside air because the sun's shortwave, high intensity radiation comes in and the windows let that energy in, but the energy cannot escape through the windows because the windows actually block that energy and trap it. So that's the greenhouse effect. And I want to say here, we hear the greenhouse effect and most people think the greenhouse effect is bad. It's not. The greenhouse effect, if we didn't have the greenhouse effect, our average temperature on Earth would be 60 degrees colder than what it is right now. So if you think about Earth's average temperature being somewhere in the neighborhood of 50 or 55 degrees, you're right away talking about all the oceans would be complete icicles or completely frozen over. There'd probably be little or no life on Earth whatsoever. So the greenhouse effect is very important to the Earth being a habitable climate for us. It's whether the greenhouse effect is changing, meaning are we changing something in the atmosphere that is going to impact how the Earth's energy budget is in balance? And if so, what is that change? So greenhouse gases, you've probably all heard about this. You probably thought I was going to talk about carbon dioxide first. Actually, water vapor is the most abundant greenhouse gas. It's also the most difficult to measure globally. And you know that water vapor is an abundant greenhouse gas because if you guys are gardeners, you know that when it is calm and clear on a cool night, that what happens is we lose all that long wave radiation that's stored up in the Earth's surface, and that all goes off into space, and our air temperature just plummets. All it takes is a little layer of clouds to move on in, and suddenly that temperature doesn't drop anymore. And it's not because clouds are an effective blanket, so to speak. I mean, they're not a physical blanket, but what they are is a layer of water vapor that actually just absorbs that energy and sends it back down to the Earth. So water vapor is the most abundant greenhouse gas, but water vapor is a naturally occurring cycle. There are some caveats about water vapor. Water vapor, warm air can hold more water vapor than cold air. So what happens is you have more evaporation, which leads to more water vapor, and thus more potential warming. Water vapor also produces clouds. Clouds can block the sun energy that comes into Earth. And so this is a very complex part of climate science. In fact, most of climate scientists are spending their time trying to understand exactly how clouds are regulating the feedback of the Earth's energy budget. Extremely difficult thing to know. There's a lot we don't know about how clouds play into our climate right now. Okay, greenhouse gas. We've all heard of carbon dioxide. Carbon dioxide is the second most abundant greenhouse gas, and it really doesn't make up much. I think it's 1 or 2% of the Earth's atmosphere. It's naturally produced. It's not something that necessarily, humans made up on their own. It's naturally produced and absorbed through the terrestrial biosphere and the ocean, meaning that plants absorb it, they store it in the ground, so to speak, or the ocean absorbs it and stuff dies and sinks to the bottom of the Earth, bottom of the ocean floor. It's out of the atmosphere. The issue is that we burn fossil fuels, and fossil fuels don't come from the air, so to speak. Fossil fuels are us digging stuff up out of the ground that has been sequestered there and then releasing it into the atmosphere. There are other trace greenhouse gases such as methane, tropospheric ozone, nitrous oxide, CFCs. I'm not going to spend much time talking about any of those since they are rather small amounts. So first off, let's talk about carbon dioxide. There is no doubt that carbon dioxide is increasing. And I think this conceptually makes sense to all of us. We put 80 pounds of gas in our car, and then a couple of weeks later, it's gone. It went out the back of the tailpipe, essentially. And so all that carbon that produced the fuel, so to speak, is essentially in the air. What we can do, and what we've been doing since the 50s, is measuring at the top of Mauna Loa at and Hawaii, because it's a good spot to measure. It's not around a lot of polluting sources, so to speak. And we can see that carbon dioxide is increasing from about 300 parts per million up to 400, and it's just a steadily increase. There's nobody that's reputable that will tell you that carbon dioxide is not increasing. It makes sense that it is. We know it's increasing. We've seen that it's increasing. We know that that's what's occurring. What the debate sometimes centers around, well, carbon dioxide has been higher in the past part of the Earth, and that's true. It's carbon dioxide has been higher, but we're talking about 400,000 years ago. What is interesting is when you look at ice cores and look at the little bubbles that get trapped in the ice cores, we can actually see how much carbon dioxide was in the past. And you'll notice that this graph here is from the year 1080 to year 2000, right around the time of the Industrial Revolution, essentially in the 1800s and especially 1900s. Carbon dioxide started going up. And again, it makes sense. We were burning fossil fuels. We expect to see that. You'll notice that this graph stops at 200. If you go back to the last slide, we were up at 410. So this graph already is way up here. So there's no doubt that carbon dioxide is increasing. But the question that people want to answer is the Earth's temperature changing? And so again, this is a whole arm of climate science. It's just dedicated to figuring out, okay, well, is the Earth's temperature changing? How much is it? They use a lot of sophisticated modeling. They use a lot of sophisticated satellites and temperature records, so to speak, to construct these temperature records. And back in the 1800s and 1900s, you'll notice that these lines indicate that the best guess for temperature is a little wishy-washy, meaning that it could have been, as high as -1 or as low as -5, so to speak. Those error bars get much less in the last 30, 40, 50 years because we have more satellite data and we pretty much can tell what the temperature is doing, especially year to year. So you'll see that we've seen about a 1.5 degree Fahrenheit increase in temperature in the last century, which is not a lot, right? That's one degree. How could that possibly be bad? And the more important question, what does that mean to our weather? And that's what I want to show you here is that here's the Earth, how much stuff is changing, how much the temperature is changing in degrees Fahrenheit across the entire Earth. You'll notice right away that most of this map is orange or red, meaning that the entire Earth, we're seeing an increase in temperature. That's to be expected. You'll notice that some areas have a much higher rate of increase, especially the Arctic region, especially over the continental areas. And if you care about Texas, which I think most of us do, because Texas, as we know, is the center of the world, Texas is actually one of the rare places in the entire world that has not seen much change in their temperature over the last century. That's actually quite surprising. So my point about this here is that the Earth's warming, okay, we got that. The Earth is on average warmed 1.5 degrees Fahrenheit. That warming is not equal across the whole area. And in fact, some areas are seeing cooling, and that's to be expected. So the Arctic region, up to 3 to 4 degrees per century. The reason why this is we believe that the ice caps are melting, so to speak, and so that there's less of that ice to keep that area cool. We're not seeing the same type of warming over the Antarctic. The Antarctic, all the ice is essentially on a continent. It's a different mechanism, whereas the Arctic ice cap is essentially over the ocean. So it's different in that regard. Again, Texas is one of the rare places that haven't changed much. And then if you take anything away from this talk on this climate change section, I want you to know that the weather in your location for a day, a week, a season, a year, it does not prove or disprove climate change from global warming. It just doesn't. You can't say that you had a bad tornado and that was global warming, or that our freeze in February was global warming, or that in 2011 when we hit 100 degrees for I don't remember how many days it was, 60 or something days that summer. That's not global warming. That's part of our natural cycle, so to speak. Now, if you were to do that every single year for a decade, you might start having a really good argument that something isn't right. But that is part of our climate. Those things are all part of our climate. So let's talk a little bit more. You may already remember, wait, didn't you say that DFW's temperature was increasing? And that's true. I did say that. Remember this graph here? We are seeing a slight warming. Let's talk about that warming. Sometimes there's localized influences on climate records that have nothing to do with global heat budgets. So this might be a little hard to see here, but what this is a time lapse of satellite of the DFW area from 1984 to 2012. And What's interesting about this is you see where DFW is right here in the center of the screen. And this place has just exploded in urban population and urbanization. And so what's happening is where we have our climate record, so to speak, is becoming surrounded by concrete. And concrete plays an important role of what our temperatures are going to be. This map here is the number of days per year with a low temperature in the 80s, or 80 degrees or higher. You'll notice that there's a little green blob right over Dallas and Fort Worth, Texas. And you'll notice that the rest of the area around our region looks like it should have somewhere between 0 and maybe 5 days per year that we are above 80 degrees for a low temperature. And if I zoom in, you'll see right away that, okay, urbanization here plays a huge role. Dallas Love Field has over 22 days per year where we expect the low to be 80 degrees or higher. DFW has 10, Fort Worth about 10. But you just go a few miles out to Mineral Wells, they have 1. You go to Cleburne, they have 3. You go to Terrell, Texas, they have 3. And McKinney, 2. I imagine McKinney's number will be changing because Collin County just continues to explode in population. So the point in this is that the DFW low temperatures have been increasing, but it's due to urbanization. It's not necessarily due to climate change from a global heat budget, so to speak. I picked this 80-degree temperature because this is a garden group, and I think most of you know that most tomato flowers or most tomato plants, except for some varieties, will not set tomato fruit when the temperatures are warmer overnight. So it may be that maybe 50 years ago, or so to speak, in Fort Worth, you could have a tomato plant that would set tomatoes during the summer, during a coolish summer, so to speak. But as we go forward in the future, we can probably expect that tomatoes will never produce here in the summer unless you get some really fancy varieties. But traditionally, they wouldn't produce because we do expect our low temperatures to continue to become warmer as we continue to grow the area in population. So another big question I always get asked, are the summers getting hotter? And I got asked this question a lot after 2011. With 2011, you can see on this graph, was a super hot summer where we had all those 100-degree days, and it just seemed like it would never end. But this is for all of Texas. This is all average temperatures for June, July, and August. And you'll notice when you look at all of Texas, there's no discernible sign here that our summers are getting any warmer. For DFW specifically, are our summers getting hotter? Yes, but that's because our low temperatures are getting hotter. It's not necessarily that our daytime temperatures are getting any hotter. Precipitation trends. Well, why is that? It's because it looks like our precipitation is actually getting wetter. We're getting more precipitation. And so here's a look at the climate stations, and anywhere blue, you're getting more precipitation per century, somewhere 6 to 12 inches per rain per century, which is quite a bit of rain actually. So this area of the country is certainly getting wetter. Because we're getting wetter is probably why we're not seeing our temperatures increase in this region. So we may be having a climate change signal here that is trending toward wetter than what we should be in Texas. And that wetter signal is also helping to keep our temperature signal kind of dampened or not increasing our temperatures. If you look out to the west in the Intermountain West in Arizona, you'll notice that a lot of stations here are seeing decreasing precipitation, and that matters a lot. Even an inch or 4 inches of rain per year is a lot of rain out there. So it's getting wetter for most of Texas. That's probably good for us. You know, we need water to have a good daily life here. Year-to-year variability of precipitation, though, is much, much greater than any climate change-induced signal, meaning that while the trend is getting wetter, we still know we're going to be prone to drought and have very dry years or very dry stretches of years. Rather, the climate change question to ask then is, will the variability or the intensity of droughts change? Not necessarily our average trend. As we know, we get several wet years in a row. It's great that we get all those wet years, but our lakes are full. We can't save that water for another year, so to speak. We really just need the precipitation trends to be what they normally are. Okay, so what are the forecasts for climate change? Climate scientists, they focus on modeling individual parameters that are known to impact the Earth's energy budget, radiation, chemistry, all of those stuffs. Those parameters are modeled by computers to give us a good idea of how the Earth's energy budget may change. We don't expect any computer to be correct, but we do expect that we have the right trend. And so here are the big climate models, and over the next 100 years, they expect our temperature to increase between 2 and 5 degrees Celsius, which is about 4 to 10 degrees Fahrenheit. And right now, we seem to be trending on the low side of this, but that's good. It's because a lot of that heat energy is being soaked up in the Earth's ocean when we're talking about atmosphere. So climate scientists, again, they're working to figure out what exactly the interface between heat energy of the Earth and the Earth's ocean is and is not, so to speak. You may wonder, well, how do we know that these climate models are right? Well, we don't exactly know that, and we do expect that they have the general trend right. But what they do is they get everybody studies every little bit of radiation science about how the Earth's energy budget works, and it goes all the way down to like the bacteria level of how bacteria influences things. And they run these climate models backwards. And they say, okay, if we can run them backwards in time and it looks like what the Earth's atmosphere looked like in 1950s, we can assume we can run them forward at 50 years and they'll be in the ballpark as well. And that's how we guess and know that. What else do climate models show? They show warmer temperatures in more area, heavier rainfall events because warmer air can hold more moisture, more frequent and intense heat waves and droughts in some areas. Again, that's that feedback loop. Fewer tropical cyclones, fewer hurricanes. And that's something I always hear on the news. They always say, we're going to have more hurricanes because of climate change. No, that's not actually true. The climate science says that we're actually going to have fewer tropical cyclones. I won't go into the reason behind that. But there is a slight signal that they might be a little bit more intense. There's no consensus on the impact of United States severe weather. What do they show for Texas weather? Unfortunately, climate models are not good enough to predict a region's climate change with any accuracy. There's some areas we do know some things about. Texas is not one of those areas that there's any confidence we know what climate change is going to do. And so this is a big problem. The individual political entities cannot prepare for what they don't know. If you were able to say all agriculture is going to fail in Texas if we don't do something, and that's how much the failure will cost, and this is how much mitigating it will cost, and maybe we'd have the political will to do something. But we don't know. We just don't know what the exact impacts will be. Sea levels are probably going to rise, but sea level rise is not going to actually be equal across the globe. The ocean is not just a big bathtub. There's a lot of things that go into where the sea levels will rise and fall and who will be most impacted. To mitigate climate change would cost money. Again, if we don't know the cost to mitigate is more than the cost to adapt to a new climate, then how do you have the political will to do anything about it? Is it fair to ask, but I think there's an ethical question, is it fair to ask that future generations pay for the cost of climate change? So that's just an ethical question. So here's the average yearly temperature in Texas. My point in climate change is that whatever climate change is, it's probably more useful for us to extrapolate what our climate oscillators that we do know impact Texas weather are to determine the future. So I drew in some stuff here that we're currently in this kind of warmish phase. We'll have warm and cold phases coming up here in the next decade or two. But I do expect that we'll probably see a slight decrease in the overall temperature because we'll be going back into that cooler phase. Now with climate change probably warming the Earth, we probably won't ever get as cold as what we were back in the 70s again. It'll be a new floor, so to speak. As the temperature increases, we can expect that if you shift that whole climate, change, if you make the whole Earth 2 degrees hotter, what it does is it shifts the whole temperature trend to where you do end up getting a little bit more hot weather episodes. I think that's probably something that we could expect to see as well. So Texas in the 21st century, any increase in temperature would mean an increase in evaporation. We'd lose more surface water. We use up more water, so that's probably an issue again. If we have greater population, it means there's more usage. Further droughts are expected to, stress our water supplies, and so that's going to be a greater concern. And again, I want to say the heat waves may be more intense if they coincide with the drought, but again, the drought's probably more controlled with our climate cycle than it is climate change. Those severe cold snaps like we had earlier this year are expected to continue, so we're not going to not see those anymore. What does climate change mean for the world? This is my second to last slide here. I think this is what everybody goes to. There's going to be some ecological or environmental disruptions in some parts of the world. That's absolutely true. I don't think there's people that will dispute that won't change in part of the world. What people don't talk about is political unrest due to the impacts on human population. And what I mean by that is if it turns out that Bangladesh, which is a country with hundreds of millions of people and only 6 feet above sea level, if the sea levels rise, then 100 million refugees are going to spill off into India and China, and it's going to be a political mess. India and China will tell those people to get lost. Those people who are just trying to subsist. It's going to be a political mess. We've already seen this kind of occur in the last few years. with Syria. They had that bad drought, and we saw refugees spilling out into Europe, and that was a big political issue. So when the climate changes in parts of the world, what we start seeing is political unrest and political issues that we all have to contend with. One thing I don't hear about are the financial ramifications of where real estate no longer has value. So let's say Miami starts to become more prone to sea flooding. Think of all the real estate that is millions and billions and trillions of dollars of real estate in Miami, all of it with a 30-year mortgage. What happens when somebody that realizes that the Earth's the sea level is rising and they no longer have property that's going to be worth anything in 30 years? What happens to that mortgage? And the financial system and ramifications of all that will spill outward to everywhere, because as we know, a lot of finance is kind of built on a house of cards, so to speak, that if you have an event like this, where suddenly all those mortgages in South Florida aren't worth anything and they were supposed to be worth trillions of dollars, that could affect a lot of people all over the world. So the summary and conclusion: the climate of Texas falls into a few predictable categories. We talked about that, and if you've lived here long enough, you kind of know that as well. Texas climate is highly variable. The extremes such as drought, hot, cold, flood have enormous impact. We know that. Any change that has occurred in our climate is dwarfed by what our natural variability is. So I'm not saying climate change isn't important. I'm saying that for our weather, climate change really probably hasn't done too much, or at least not too much bad, and is dwarfed by what is naturally our weather. The DFW area is getting warmer. It's primarily due to the impacts of urbanization, and Texas is wetter on average due to climate cycles and/or climate change, but precipitation trends aren't necessarily as important as the year-to-year variability, again, which is controlled by our natural climate. And finally, we don't have the answers to what lies ahead, but if you think we probably shouldn't risk it, then we probably should do some mitigation efforts to try to disrupt or get ahead of what we perceive as global warming and climate change. Thank you very much for having me.